are already at half the ladder, and we're gonna go and see more blah, blah, blah. So good. So hello everyone, welcome to Foundations of Language Technology, lecture number 10, Learning to Classify Part 2. Today we're going to talk about different classifiers that are popular in the NLP community. We're going to see 3 different ones, and in addition to that, we're also going to see how to evaluate different classifiers. So we start out reversely. We start out with the evaluation. So the evaluation basically means to assess how good our classifier is, and this may absolutely not be underestimated, because in the NLP and data science machine learning communities, we always design different classifiers, different machine learning algorithms, and if our evaluation is not good, we may not be identifying the latest state of the art, which is actually the goal of large portions of machine learning and data science. So what is the setup in evaluation? So we want to assess the performance of a learned model, for example, by estimating the error on a given reference data set. So typically we talk about the error. We could also talk about the quality. So this would, let's say, the quality would be, let's say, 80% accuracy. When we talk about the error, we would say this is 20% error. And we have a data set, and this is some reference data set, which is already labeled and annotated, and we compare our classifier to this data set. So this reference data set is also called the gold standard, and it is typically annotated by human subjects. For example, this could be an expert. Let's say a philosopher or a social scientist could annotate the data set. There are also another option where we instead have crowd workers. But in general, there are different options, what kind of background those humans could have. Ideally, of course, we have expert annotators. And what we then do is what I've already said, we compare the predictions of our classifier with the gold labels in our gold standard data set. And this yields the error or the performance of our model. And when we estimate the error of our model, we can differentiate between 2 different aspects of evaluation. The first one is for model selection, the other one is for model assessment. And these are the 2 goals of evaluation pointed out in Hasty et al. So what is model selection? What we have there is we estimate what we can also call then the prediction error of different models in order to choose the best models. Just assume we have focused in on one different model, let's say a neural network or a decision tree, but this is parameterized by different parameters. For example, the model could have different features, it could have different parameters and hyperparameters. And now we have a whole family of models, and we want to find out the best one by choosing or by iterating over different features, over different parameters and different hyperparameters. By the way, what is the difference between parameters and hyperparameters? A parameter is what is part of the model. If we talk about neural networks, for example, we have weight matrices, and those are part of the classifier. But then there's also something which is not directly part of the classifier itself. For example, there's a way to optimize neural networks, which is gradient descent, and this also has different parameters. For example, the learning rate, but this learning rate is not part of the neural network, so that's why we call it a hyperparameter. And typically, when we do an optimization, when we do model selection, we have both parameters and hyperparameters, and we choose them during model selection. And then finally, once we have settled on a model, we assess its generalization performance. So we want to see, here's a new data set, how does it perform on this new data set? And this is called generalization performance, because we want to see how well does it generalize to unseen data. Now, let's assume we have a lot of data. What we would then do is we would split our data in 3 parts, and we would do the splitting randomly. And those 3 parts are first the training set, where we fit the parameters of the model. And then we have the test set, the def set, we have the def set. And on this def set, we can choose, we can evaluate our model that has been trained on the training set for different feature combinations, for different hyperparameters, and for different parameters as determined on the training set. So that's why we have the def set 4 to do the model selection and to determining the prediction error. And then finally, we have the third part, which is the test set, where we estimate the generalization error of our model. And what is important is that the test set must be kept secret. So you can only use it for assessing the generalization performance. You cannot use it for doing any hyperparameter tuning, for doing any model selection. Because if we would do it for model selection, then what would happen is if we would optimize our model on the test set, then we would substantially underestimate the true error. For example, we would find out the model has an error of 10%, but in reality, if applied to a completely new data set, as the user that is later using the model, so the user would be applying the model on a completely different data set, then the user would get a much worse performance, 30%, because the user didn't optimize, and the user cannot optimize the model on this new test set. So that's why we may not use the test set for evaluation of the generalization error. And also note that this is really a very, very important issue and something that is often neglected and often treated in a wrong manner by practitioners of machine learning and also by new incomers, that they really optimize on the test set, that they tune their hyperparameters so that they get good performance on the test set. But we need to point out that this is unethical, misleading, and inappropriate. It's unethical because you would report a good performance of your model or a much better performance of your model than your model is actually doing. It's also misleading because it would suggest that your model is much better than it actually is, and it therefore it's inappropriate also. By the way, why do we choose a random divide of our whole data set into train, def, and test? We do it randomly because if we do not do it randomly, then it might turn out that our test set is not representative of the data, right? Let's assume we have data ordered, we have a corpus ordered in a temporal manner, right? Let's say it spans 5 years. And as we can assume, over time, things are changing, right? Things are changing in language, for example. If we do not split the data randomly, but if we do a particular selection, let's say we just do evaluate on the year 2020 or on the year 2015, only on one of those years, then we can assume these years have different properties, and our data would not be, this subselection of the data would not be representative of the whole data distribution. That's why we would typically do a random division of our data into 3 parts. So what are considerations for creating a test set? Of course, it has to be distinct from the training set. You cannot put in the test set something that has already occurred in the training set, because the model could just memorize what was in the training set and then be good in the test set because of memorization. But this is not what we're going after. We want really to see whether our model can extrapolate to novel data instances and whether it can generalize to such novel instances. The test set needs to be large enough to be a good representation of corpus. Go into the extreme case where the test set consists of only one data point. So we could be lucky and label this data point wrongly. Our model could be lucky, or it could be unlucky and label it incorrectly. So it would either have an error rate of 0, an error rate of 100. But this could just be chance, that this model was not very good on one data point, or that it was by chance very good on one data point. So just having one data point is certainly not appropriate. Also compare it to students, to an exam for students, right? So if we would have just one single question, the result would be very random, because somebody could just by luck not be good on this single question, or could be very good on this single question, therefore perform very well, but this would not be representative of your true capabilities. So how large does the data set has to be? There's a rule in statistics, there's some heuristics in statistics which says that you should not trust a sample below 30. So let's say this is a very coarse heuristics that of course in any particular situation can be wrong, but we can argue that everything that's smaller than 30 is certainly not worth it and will not yield good statistical, does not have good statistical properties. Typically, the sizes of test sets in standard NLP applications is a couple of thousands or at least a couple of hundred, but even this could be too small. But if you have like in the size of a couple of hundred, couple of thousand, then that's already much better than 1, 10, or 20 data instances. And of course, the test data should be representative of the full problem, right? As we've already said, if there's a temporal ordering of the data, the test set should not just be from 1 year, right? Where this 1 year would have particular properties, or the test set should not only consist of female or only of male persons, for example, if we want to classify a person, but it should be representative of the whole population. Okay, so what is one nice way of, or one convenient way of doing validation, model assessment, model evaluation in the face of data sparsity, and this is cross-validation. So here we have a typical situation nowadays, or until nowadays, maybe that's going to change in the future, but we still have, for most problems, very little data. So data is sparse, so they cannot get good strain depth and test splits, and the test set would overall be just too small to get reliable results. That's a couple of dozens test instances. So what are we going to do is we're going to do cross-validation, and in cross-validation we're going to use a running test set to increase the training data, and maybe also to increase the test data, right? So that we have a better estimate of our model. And let me say at this point that there are different ways of doing cross-validation. I think in the NLTK book, there's a particular way outlined that's differing from the way we're doing it here. So there's, for example, something called nested cross-validation. So I just focus on one particular implementation of cross-validation. And what do we do for there? So a typical approach to cross-validation is called, or the most classical, most standard is called K-fold cross-validation. What we do there is we divide our whole data in K equal size folds, K equal size parts. We train on K-1 folds and compute the test error on the remaining folds. And when I say the training, then it includes both the train and the def set. So we do the training on K-1 folds. A part of the fold is used for the def set to optimize the model hyperparameters and the features, and to do the model fine-tuning. And then we calculate the error on the remaining fold. And we do this K times, such that each fold is used exactly once for the validation or for the model generalization. And it's also important that thereby we look at all points in the data. So all points in the data one time become part of the test. And then in the end, we do the averaging, right? We do the average, we get an error on each of the folds, and we take the average to get the overall performance of the model. And here how it's looking graphically. So so this is for tenfold cross-validation, which is one of the most popular manners. So why tenfold? Tenfold is a good compromise between, well, if we do this more often, if we do tenfold cross-validation, if we do it more often, then potentially we get a better estimate of the error because we do more averaging. And also we do have a larger train set. So yeah, so our model would be using more of the training data. So we will use more of the full data to do the training. That's the positive thing. On the negative thing, it's also more costly. So here we need to train 10 different models. If we would do only 5-fold cross-validation, we would only estimate 5 different models. So, and this increases the cost, but 10 is like a good. So what you see here is this is the train set, the train plus the test set, and then we evaluate here, and then we iterate through here in 10 different runs, and our full error is just the average error over those 10 runs. So good. So that's this part. Let me now talk about. So this was like a meta aspect of evaluation. Let me now talk about which kind of evaluation metrics are we using. So there's certain metric how we're going to evaluate our NLP system, and this metric depends crucially on the kind of task that we have. So we have machine translation. This has certain metrics. We have like summarization or more general text-to-text generation, which is not part of this lecture actually, but that's also a very important problem in the NLP community. We have certain evaluation metrics in this area. And then if we have regression, like if we estimate the size of a person or the weight, that's going to be called regression. And then we have certain metrics. And now in this part, in this lecture, we're going to do classification. So for classification, we'll have certain metrics. One of the most popular is one of the most simple is called the accuracy. So we check how many correctly classified items do we have divided by all items. So now this gives us an accuracy. We could do 1 minus to get an error, right? If we have 80% correctly classified, then 20% are erroneously classified. So how would that look in NLTK? Let's assume we have the NLTK naive Bayes classifier that we're going to see later. We have our train set. We train our classifier, and then we just say NLTK classify accuracy using the test set and a classifier, and then we print it. We find that we get, in this case, 87% accuracy. Now, what is the problem with accuracy? Accuracy is very simple, but it has some problems, and that's what we're gonna see in this slide here. So one problem is we take the frequency distributions of labels into account, and we need to take the frequency distribution of labels into account. And in particular, what could be is that there is a most frequent label baseline. So, and we make here an example of word sense ambiguation, where we have a corpus and we have the word bank in it. And we want to classify each instance of the corpus, whether it's a financial institution or whether it's a river bank, right? And let's assume our corpus is a news corpus, and it has like 95% of all instances of bank are referred to the financial institution, right? So we would very easily get a baseline of that has 95% accuracy that's apparently performing very, very well. They would always say, well, it's the financial institution. So now the problem is, if we have a classifier that is having a performance of 97%, that looks impressive, but we need to keep in mind that it's very easy to get 95% by just always guessing the financial institution, right? So, and this is something which can be misleading about accuracy, that we can get very high numbers that do actually not mean very much in terms of the frequency distribution of the data, namely that a majority of instances could be of one class. Good. And in contrast, if we did have a balanced corpus, where all the, let's say we have 5 different senses, one being the financial institution, which occurs in 20% of the cases, and all the other senses occur in the remaining 80% of the cases, then we see that each that like the most frequent label baseline would be much lower. It would only be at 20%, and then getting 90% accuracy would be much harder. So what the takeaway is, if we have a balanced corpus, then accuracy is actually a good measure. But if we have a very imbalanced corpus, where most of the instances are from one class, then the accuracy can be highly misleading, right? So this is the takeaway message.